Today we're going to talk about a new topic, which is recursion. It's a really fun topic, so you will get to enjoy it. And it's not difficult, but it needs a little bit of imagination. You need to be able to imagine how recursion works. But it's a really powerful mechanism in programming. And you will get to use it a lot, right? So it makes, writing some programs very easy compared to writing iterative algorithms. We'll understand the difference between the two. Okay, so what is recursion? We'll start with few interesting things to explain what recursion is. If you search on Google for recursion, I encourage you to do that now if you want. I'll do it with you. I'm going to go here and say recursion. What does it do? It tells you, did you mean recursion? And then if you click on it, it takes you again to the same page, and it takes you again to the same page, and it takes you again to the same page. That is really what recursion is. It's basically something that I repeat over and over and over again until I hit, some base case. Yeah. So Google is kind of trying to play a joke by doing this. Of course, right? I'm writing the spelling correct, but it still gives me this link, and if I click on it, it just takes me to the same page over and over. Yeah? There are other examples of jokes around recursion. So the recursive light bulb joke, right? So if you look at this one, how many twists does it take to screw in a light bulb? It says if it's already screwed, then 0, because it's already screwed. Yeah. If not, then twist it once and ask me again. That's again recursion. I'm repeating something. Yeah. So I'm doing a step and then repeating, a certain task. Or you could see this one, right, where it says, another example you could imagine of recursion. These are like the 3D printers, and imagine 3D printer printing 3D printers. Yeah, this would be another example of recursion, and so on. So we know so far something called iterative algorithm. That's the algorithms we've been using. These ones are the ones that include repeating steps in an algorithm or a recipe using loops, whether for loops, right, or while loops. So these loops lead to what is called iterative algorithms. Yeah, they repeat, a certain number of steps, a certain number of times. So iterative algorithms that contain loops consist of the following steps. You have to define a stopping condition, otherwise the loop will go indefinitely. You don't want that. You don't want an infinite loop in your program or algorithm. Yeah, so you have to specify a stopping condition. For instance, range of a certain number, or until a certain condition is no longer true, using a while loop. Yeah. And then you have to specify a stopping condition, and inside the body of the loop, what is going to be repeated, yeah, as long as the stopping condition is not met. So to write an iterative algorithm, all you have to do is decide these two steps. What is the stopping condition, and what is going to be repeated? What computations get repeated? Okay? Good. I don't remember what I was saying, Rawad, right? Sorry, I just saw the message. Okay. Let's start with an example. You remember the factorial? So, writing a program to compute the factorial of a positive integer n. We define factorial as follows, right? We all know this from high school, that factorial of n is n times n minus 1 times n minus 2 all the way till 1. Yeah, and we know how to write a program that does this, an iterative program. So here is a function that is iterative because it uses a loop, and it computes the factorial of a number n that I pass as an argument or a parameter, and returns this to the caller. Okay, so I start with some initialization. So factorial is equal to 1, and then loop from n till 1. Right, so the step is minus 1 here, so I go n minus 1, and so on. And I keep accumulating this multiplication inside factorial. So I'll multiply factorial, current value of factorial, by the current value of I. So first time it will be n, next time it will be n times n minus 1, n times n minus 1 times n minus 2, and so on. And at the end, return this factorial value. Okay. Just to remind you, I'll open the iterative factorial. And let's test it, right? So I'm gonna run it. Okay, for some reason it printed 1, even though I give it, wait a second. Yeah. Right, I'm not saying the step correct. And it gives me 120, which is the factorial of 5. If I try it with 3, it should give me 6. Okay, and so on. So that we have done before. Okay. So what's happening here? This is the stopping condition when I reach 1, right? So because I write stop right before 0, which is 1, so I'm going from n till 0. That's what gets repeated, multiplying, whatever value n factorial currently is times current value of I. Now, let's see, how can I write the same program in a recursive manner? Yeah. So this is another way of writing the same program, which is computing factorial. What are recursive algorithms? Recursive algorithms solve a problem by reducing it into smaller, simpler versions of the same problem. Yeah, that's really in a nutshell. Let's see, what do I mean by this, right? So I keep reducing the problem. I start with a big problem, like computing the factorial of n, and I keep reducing the problem until I reach a simple case that I know how to solve directly, yeah, without any, sophisticated computation. Okay, the first step, which is reducing, the large problem into smaller problems, is called the recursive step. And the second step, which is, hitting a case where I can solve directly, is called the base step or case. Okay. And all you need to do is to find these two steps. In any recursive algorithm that you're going to write, you have to think about two things. What is the base step or, base case? So simple version of the problem that I can solve directly. I know its solution. And the recursive step. How do I take a bigger problem and reduce it into smaller version of the same problem until I reach the base case? Let's see an example of this using the factorial. Okay, so we know factorial of n is n times n minus 1 times n minus 2 all the way till 1. Great. We need to do two steps, the base case and the recursive step. Okay, so the base case. What n do we know the factorial of? Can anybody tell me? If maybe for 5, it's difficult, I have to do the computation, but there is, something, that I know the factorial of directly. Yeah, doesn't need any computation. Any thoughts? Factorial of 1, correct, right? Factorial of 1 is 1. Yeah, so basically I don't multiply anything. I know that, right? If you give me 1 as an argument to the function that computes factorial, I should return 1. Hard coded. So basically factorial of 1 is 1. So when n is equal to 1, you should return 1. Great. The recursive step, how to write the problem in terms of something simpler, yeah, until you reach the base case. So if I give you a value n, any integer, positive integer n, can I write it, right, the factorial of n in terms of, a simpler version of the problem, right? So something that takes a smaller input, yeah, to compute the factorial of, somehow, right? So this is simple, right? We know that factorial n is n times n minus 1 times n minus 2 all the way till 1, right? If I take this part, this thing, yeah, so factorial of n is n times, what is this? N minus 1 times n minus 2 times n minus 3. I'm really sorry, Saad, I don't know what to do. Yeah, so it seems the internet is really hard. I'm at AUB, right? This is the best internet speed I can get here in the country, so I'm not really sure what to do. I can try to, let me try. I'll try, I don't know if that is gonna work. I'll try to use the DSL. So back to my question. What is, yeah, exactly, right? So n factorial is equal to n times, n minus 1 times n minus 2 all the way till 1. I can also write n factorial as n times, what is this thing that I've highlighted? So Rawad is saying it's n minus 1 factorial. That's correct, right? So I can say that if n is greater than 1, if you give me any value n greater than 1, I can express n factorial as n times n minus 1 factorial. What did this do? It allowed me to, if you give me 5, I'll compute it, right, as 5 times factorial of 4. Yeah, and solve it for this. So I solved the problem for a smaller input, which is 4. And factorial of 4 is what? Is 4 times factorial of 3. Factorial of 3 is 3 times factorial of 2. Factorial of 2 is 2 times factorial of 1. I know how to solve factorial of 1. Right? So basically, I keep reducing my input until I reach the base case. Okay, let's see how do I write this in code, write the whole program, run it, and then understand how it works. So if n is equal to 1, right? If you give me n as 1 as an argument, I know what to do. I return 1. I know factorial of 1 is 1. Else, if n is greater than 1, right, you return n, and then call yourself again, so the same function calls itself factorial with n minus 1. Yeah. So basically, the recursive step, the function calls itself. So far, so good. Is the lagging better now? Okay, great. I'm glad that it is. I'll try to use the DSL from now on. Maybe it's better. Okay, great. All right. So let's see the whole program. Okay. So here is the function, right? It's a recursive function. I called it factorial, and it has 2 steps. The base case, if n is equal to 1, return 1. Okay. And then it has the recursive step, right? So if n is greater than 1, any value greater than 1, that's not the base case. I will go into the else, and I return n, and I'm calling myself again, right? So this is really the key to recursion, right? I'm calling myself. This is the same name as this, right? As if I'm calling the function again with a smaller input n minus 1. And the goal is to I keep doing this recursively, so repeat, 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 as if it's an iteration or a loop, until I hit the base case, because I'm reducing n by 1 each time. So the start was 5, then 4, then 3, then 2. Eventually, it will hit this base case. I know how to solve this problem, and then I backtrace to get the actual value. I want to run it, and then we're going to do it step by step to see exactly what the interpreter is doing. Okay. Let's do the following. Let's open the code. Factorial recursive. Okay. Here is the function exactly as in the slides. So basically, write a base case and a recursive step. And I'm calling the function again with smaller input. Here I'm going to do the following. I'm going to take the input n, the value n from the user as an argument, command line argument, and then I'm going to run the function and see what it gives me. Does it calculate factorial correctly or not? Python back.py, and I'm give it 1. Let's test the base case, and it gives me back 1, right? Because it will get here. Yes, n is equal to 1, so return 1. So that's the trivial case, the base case. Okay, let's give it 3, and as you see, it gives me 6. Let's give it 5, and as you see, it gives me 120. 4 gives me 24. So it seems to be working correctly. Okay, how? Let's understand how. What about 0? So here, I'm assuming that it takes as an input, right, a positive integer. I know that factorial 0 is 1. But here I'm assuming that n is a positive integer, so I'm giving it a positive integer. Positive integers start from 1. Yeah, this one would return. If you do it with 0, it will cause some issue. Yeah, so you can try it. will not work well, right? It gives you an error because it assumes here it takes positive integer. Of course, you can modify the code to have two base cases. If n is equal, or if n is less than or equal to 1, return 1. So the simple case to solve it is to say this, n less than or equal to 1, return. Right? Now, if I run it, it gives me 1. No matter what, I give it 0. Or, okay, Adam? But at least what we were assuming is that it takes a positive integer. Okay. Other questions? Good. Let's understand. This is very important slide. Please follow. How are recursive functions executed? We're going to use our example, so the factorial, to understand this. Okay. So I have, how do I hide this thing? Okay. Yeah. Okay, great. So here's the function. It's factorial n, right? And then we have the code as exactly as on the slides. Let's see how the Python interpreter executes this. Again, remember the scope, right? So I have a global scope which sees fact, right? So far, right? It reads, like this. So it will see factorial. The factorial means that, there is a function called factorial, which corresponds to some code. It's not going to dig into it, open it until it's called. Then comes print factorial of 4. That's a calling of the function. So passing n equal to 4. That will open the f scope, the factorial scope, right? Okay. So n is going to be equal to 4 because I know I passed, n as 4 from the global scope. Okay. So it assigns n to 4. Place in memory, call that with the value 4. Okay. Then it executes the function. It checks, is n equal to 1? 4 is not equal to 1, so it's going to get into the else. Right? So it's going to get into the else. So it's going to get here, and it's going to return 4 times fact, right, of n minus 1 is 3. So it's going to do this, right? That's what it's going to execute. Basically return 4 times factorial of 3. Okay, great. Now, what is factorial of 3? That's another call of the function fact, passing n equal to 3. So I'm going to open another factorial scope now for this one, for this factorial of 3. Yeah. For this factorial of 3. Yes, you should always have a step, right? A base step, which allows you when to stop execution. Otherwise, you'll keep running indefinitely, like an infinite loop. We'll see this in a bit. Okay. So back, right? I called factorial 3. That means, open another scope for the function, this time with n equal to 3. So I have a variable called n in memory with the value 3. What does it do? It checks, is n equal to 1? 3 is not equal to 1. So it's going to get here, and it's going to return 3 times factorial of 2. What does factorial of 2 do? Opens a scope, right? Another fact scope with n equal to 2. What happens? N, right, is equal to 2. That's not equal to 1. So it's going to get into the else, and it's going to return 2 times factorial of 1. Okay. Now, factorial of 1 is another call of the function. That means open another, f scope, right? Where n is equal to 1. And now I hit this guy, right? So I hit the base case. So basically, yes, n is equal to 1. What do I return? Return the value 1. Okay. So return the value 1 to whom? To the caller, right? I hit the base case. I'm sure, n is equal to 1. So I'm going to get into the if, not the else, and return 1 to the caller. Turn back 1 to the caller. So this factorial is going to be replaced by, 2 times factorial of 1. I've already returned, I know factorial of 1. It's equal to 1. I returned that, right? So I'm going to return 2 times 1. That's 2. Why do I return it to? To the caller. So basically now I'm returning 2 to this guy. So replace factorial of 2 by 2. Okay, so now I'm returning 3 times 2. That's 6. Who I return this value to the caller. So now I get 6 here. Okay, so I now return 4 times 6 to who? To the caller. That's this. All right, so I'm going to return 24, and then I'm going to print 24. Okay. Let's take some questions. Let me see, where's the annotate? Here. And time to take questions. Did you understand what's happening? Okay. Anybody has questions? Okay. We'll see a lot of examples on this, but I hope you got, the intuition or the hang of it from this example. Okay. So again, right, the important thing is you have to define a base case to stop, calling yourself, and you have to define a recursive step where you call the function, again, or the function calls itself. So using the same name exactly, but with smaller inputs, yeah, until hopefully reach the base case. Okay. Let's do another example if you have no questions. Multiplying 2 positive integers. Yeah, so I want to write this basically if I, recursively. Of course, I can say just print A times B. Yeah, I don't need anything else. But I'm trying to think, give you an example about how, to do things recursively. So I want to write a function, a recursive function, takes 2 inputs, A and B, and it tries to return back A times B. So how do I think about this recursively? The first thing to notice or observation to make is the following. A times B is the same as adding A to itself B times, right? So I can write it this way. A times B is A plus A plus A plus A, B times, yeah? So if you give me 3 times 2, it's, adding 3 twice. 3 times 5, it's adding 3 5 times, yeah? So I use this observation to try to express multiplication as, a recursive function. So what is the recursive step? What do you think, right? I want to be able to say A times B is equal to, or assume there is a function called multiply that takes 2 values. All right, so I have multiply or M that takes 2 values, A times B, A and B, sorry. Okay. And I want to express it as, right, this multiplication, A times B, as something, right, that uses M of A and B, or calls, the function calls itself with smaller values of. So what do you think? Any thoughts? What is this? So A times B is equal to A plus. Can you express this as a multiplication? A plus A plus A, B minus 1 times. Yes, it's exactly as Adam and Rawad is saying. So this is A times B minus 1, right? So I can express A times B as A times B minus 1 plus A. Yeah, so I can write it as follows. A plus M of A and B minus 1. Right. Okay. Sorry, my annotation is horrible, but I'm using the pad. So again, multiplication of A times B is nothing but A plus multiplication of A times B minus 1. Okay, that's what it's trying to say. Okay, what is the base case? Yes. So basically, that's right, M of A. If I multiply A by 1, I should get A. Right? That's the base case. Right? So I can keep reducing B. If I have B 3. I want to reduce it to 2 and then to 1 until I hit the base case, which is 1. Okay. Let me clear this and show you, on the slide. Okay. So as we said, right, A times B is A plus A times B minus 1, or adding A, B minus 1 times. So that's really the recursive step, right? That A times B is equal to A plus A times B minus 1. Okay, so the base case, as you guys said, if B is equal to 1, A times B is equal to A, right? Because A times 1 is A. And the recursive step is B, if B is greater than 1, any value greater than 1, then just say add A to A times B minus 1. Okay, so let's try to write this function together. What is the first line? Can somebody tell me? Other than Rawad and Adam, anybody else? Any thoughts? What is the first line you're going to write in this function? The base case, right? Well, how do you write the base case? It's already written. Yeah, but how do I write it? What is the, if B is equal to 1, correct? Muhammad, right? What do I do? Yes, Daniel. Return A, exactly, right? So B is equal to 1, return A. That's excellent. Okay, the recursive step, else, yes. Can you tell me? So else means, right? So else means B is greater than 1. You don't need this additional condition. Of course, you can use it, but you don't need it, right? Else meaning what? Meaning the above condition did not happen. So B has to be greater than 1, assuming that most of them are positive integers, of course. So else, yes, what do I do? What do I return? Look at the recursive step. Try to express this in code. So else, I have to return something. A function has to return. So return, okay, and then yeah, but this is correct. You get the understanding, but you're not able to write it in code. I have to call the function itself, right? I'm not going to multiply A times B minus 1. I'm going to return A plus multiply exactly as Michelle is saying. A comma B minus 1, or Rawad is saying. Yeah. So else, right? Return A plus you have to call the function again. Otherwise, it's not a recursive function anymore, right? So you have to, I want to call the function again with 2 values, A and B minus 1, and accumulate, right, already. And okay, so don't, it's always about calling the function again. Yes, correct, right? Some of you have said it's A times B minus 1. You got the hang of it, you understood it. But if you do this, this is going to be multiplication. It's going to multiply A times B minus 1. So it's not a recursive function anymore. The whole point is to keep repeating, calling myself until I hit the base case. So if now I give this function the value, I run it right with the value, like let's say A is 3 and B is, or A is, sorry, right, let's say 2 and B is 3, what is going to happen? It's going to check, is B equal to 1? No, B is equal to 3. So it's going to return 2 plus, call the function, right, M with the value 2 and 2. Okay. All right. So now it goes and check. Is B equal to 1? No, it's equal to 2 now. So it's going to return, right? Like the M is going to be 2 plus M. 2 and 1. And now that hits the base case because B is equal to 1. So it's going to return 2. And so finally, I'll return 2 plus 2 plus 2, which is really 2 times 3. Okay? That's how it works. Want to run it? Let's try it. Okay, where is it? Multiply. Here it is. Yeah, that's the same code. As you see, it gives me 12 because I'm giving it 4 times 3. Yeah, so Let's try to something else. 5 times 8. Let's see if it works correctly. And it gives me 40. Okay. Questions? Okay. So remember two things in a recursive algorithm. Yeah, base case and recursive step. And in the recursive step, you call the function calls itself. Yeah, of course, you can you import right this and give it to integers right. Yes, of course. I just didn't do it here. So I'm changing it directly from the code. Okay. Other questions? Let's do another exercise. I want you to, if you have a paper, beside you and a pen, please try to write this program, right? So you have to think about the base case and the recursive step. And again, remember, recursive step means you call yourself. We want to write a program to recursively compute the power of, raise a to the power of n, where a is, let's say, a float and n is a positive integer. Yeah, or two, both of them are two positive integers. Yeah, to stick to the same style as the slide. So basically, what does this function do? It will take two values, a and n, and return a, to the power of n. Of course, I could use this operator in Python, but I want you to write a recursive function. So think about it. Yeah, what is the base case? What do I know the power of? Immediately without any computation, and how can I reduce this problem? To a smaller version. Please think about it. Take your time. Before you share your answers with everyone. So I see that some people are asking if the base case is a to the power of 0. It could be, but here always look at what is the function assuming to take. It takes two positive integers. Is 0 a positive? No, right? So then think about what is the smallest positive value that I can solve this problem for. Yeah, a times 1, for instance. So I just say, because I'm assuming that both a and n are a positive. So the base case is what? Yes, I see that some of you are already thought about that. What is the base case? If you give me n equal to 1, what should I return? Yes, Ali, right? Or before. Return a. Excellent. So that's the base case. Perfect. If n is equal to 1, return a. That's absolutely right. The recursive step. How do I express a to the power of n in terms of a smaller version of the same problem? So if n is else, right? So if n is greater than 1, what should I do? Okay, I've seen some answers. Not Ali, so Ali saying it's a times a times a n times. No, right? So that's the original thing. That's the definition of a to the power of n. It's a times a times a n times. Now in the recursive step, you have to express this in terms of n minus 1, for instance. And you want to reduce the problem. So it's a times, right? A times a times a n minus 1 times. How do I write this now recursively? Yeah, assuming the function is called power. Okay, a times power a n minus 1. Okay, any other people? Adam, say the same. Okay. Other people? Who doesn't see this from the chat? Okay. Let's see the solution first. So what is the base case? Again, what is the smallest? The question to ask yourself, what is the smallest value of n from the domain of n? Here it's positive integers, for which I know the power a to the power of n. That's, as you guys said, when n is equal to 1. Right? What is the recursive step? The question you ask yourself, how to make the function call itself with smaller values of n until it reaches the base case. Excellent. So you guys said a to the power of n is equal to a times a to the power is equal to a times a to the power of n minus 1, right? Because we know, right, this from mathematics. So here's the function. If n is equal to 1, that's the base case, right? Return a. Else, return a. Call yourself again with the value n minus 1. Yeah, so power of a and n minus 1. Okay, excellent. Let's run it, and then I'll take questions. So it's called power, I think. Okay. Let's see. Let's make it, take 2 arguments so that we can run it directly. So put this and then power. Let's say A is integer this argv of 1 and as int sys argv of 2. So I'm just reading the A and N from the command line, assuming both are integers, and then A and N. Okay, let's try it out. So Python power pi. Let's try maybe 2 and 5. What is 2 to the power of 5? Anybody knows? 32, exactly. I think it gives me back 32. Let's try 5 to the power of 3. Any thoughts? What is 5 to the power of 3? 125, correct. Right. And so on. Let's try it with 1 to make sure that it works. 5 and 1 gives me back 5. Okay? Makes sense? Okay. So how does it call 5 and 3 when I do power 5 and 3? Right, so if I give it, 5 as input and 3, it will go here, n is not equal to 1, so it's gonna multiply 5 times power of 5 and 2. Right, reduce n by 1. So power of 5 and 2, let's call the function again. N is not equal to 1 because 2 is not equal to 1, so it's gonna return, this would be replaced by 5 times power of 5 and 1. Yeah. So, and then this hits the base case and it returns 5. And so it will multiply 5 times 5 times 5 and return 125. If we have it return 8 to the power of n, then this is not a recursive method anymore. Yeah. So this beats the curve. So what Mohammed is saying the function does the following. Just gives me back, definition of power of a n, right? Instead of writing all of this, I say return a. Okay, yeah, that would work, right? Because I don't even need to write a function. I could just say print a to the power of n. But what I'm trying to do is to write this in a recursive function. Yeah. So I'm trying to give you an example. Of course, you don't need it, right, for this particular case. But I'm trying to, have you practice how to write a recursive function. Yeah. The same thing we did with before, right? Like summing the elements in a list. I could also do sum of L, but I could also write a code, that loops over every element in the list and tries to sum them. Yeah. So we're teaching you how to do things. It's not that you really need it for this particular example. Okay. Yeah, this is basically the concept. We're trying the concept. Of course, right? If you want to solve this problem, you could just say a to the power of n, return a, double stars, n. That will solve the problem. Okay? Other questions? Okie dokie. One more exercise, maybe, or summary, and then we'll do a couple of exercises, and we'll stop here and continue on Wednesday. So again, I'm going to repeat this one last time. Here's a summary of recursive functions. You define 2 things. The base case, right? So, and the recursive step. Okay. So to do the recursive step, you implement it by making the function call itself on simpler input. That's the key, right? Whenever you're doing a recursive step, you know that you're actually doing a recursive step by making the function call itself. So if it's called x, you have in the recursive step, you're calling the function x with smaller input. To avoid infinite recursion, so making sure, right, that your program will finish or your function will finish for a given input, you have to make sure that there are at least one base case, and you can have multiple base cases. So there's no problem to having more, and we'll see how. Yeah, and the the recursive step must must solve the problem on smaller input, until you reach the base case. That's basically it. Otherwise, you will get into an infinite recursion. Let's see examples of this. I've given you two functions, and I want you to spot that. Both are recursive. Why are these functions recursive? Can somebody first tell me why? I mean, I'm calling these functions recursive. Let's focus on the first one. This function, why is it a recursive function? What tells me that it is a recursive function? Because it calls itself. Inside here, I'm saying, f of n minus 2. So if you give me n equal to 5, I'm going to return 5 plus 5 minus 2, that's 3. And I'm calling myself again. That makes it immediately a recursive function. Same thing for the second function. So let's focus on the first one. This function has an issue. A gamma is saying, yes, it's infinite. Why is it infinite, a gamma and Ferry? Yes, there is no base step. So the problem is this function has no base step. So what's going to happen is if you give it 5, f of 5, right, it's going to call itself. So the first time it's going to return 5 plus f of 3. And f of 3 will do the following, right? 5, so it's going to be 3, sorry, right, plus f of 1. And then f of 1 is going to be 1 plus f of minus 1, and so on infinitely. So I'll go into as if an infinite loop, right? So basically it's going to run forever. There's no base case. I'm going to keep calling myself, non-stop, right? There is no place to stop me. I'll keep just reducing n by 2 until I hit minus infinity. Okay? So no base step, that's a problem. Okay, let's focus on the second one. This one. Okay, again, it's a recursive function because of this. I'm calling myself. It's obviously as a base case. If n is equal to 0, I should return 2. Else, return n plus f of n plus 2. Okay. So, any thoughts why this is problematic? I see that Agama already got it. He said, the correct solution to me. So last step should be fn minus 2, never gets to the base case. If the initial n isn't 0, then, right, let me see what you're saying, right? Because it's increasing. If the initial n isn't 0, then it will keep going. All of you are correct, right? The problem is here, there is a base case, but I'm never reaching it. If I give the function, n, so I call the function with f of 5, it's not the base case, so I'm going to get here, and I'm going to return 5 plus f of 7, okay? And f of 7 is going to be, okay, 7 is not equal to 0, so I'm going to return, 7 plus f of 9, and so on. Keep going till I reach infinity. I'm never reaching the base case. Yeah, so that's really the problem. It's infinite, exactly. yeah, of course, right? What Chad was trying to say, right, when she said f of n minus 2, is that right? I really should try to reduce the value till I reach n equal to 0. What Rawad is saying is if it's odd, right, I might not even reach n equal to 0. Good point. Yeah, but I think the intuition Saad had was correct, which is I should really reduce the value rather than add it. Otherwise, I'll never reach the base case. So for increasing functions, the base step should be upper bounded. So you mean like something like this, right? For n, yes, then you would have to say when n is equal to 100, for instance. Yeah, that's what you mean. Yeah, good point. Other questions? Other thoughts on this? Okay. Let me clear. Okay. Let's see, what do we have here? So here, no base case, as you guys said. Here, the base case is never reached. Okay. We'll stop here. I'll take more questions if you have. Otherwise, we'll talk on Wednesday. Was it better after I connected to DSL? So the lagging is better now? Okay, good. Perfect. Right. So I'll do that from now on. Okay, guys. See you on Wednesday.